Okay, just looking at the last section, tangents to circles. So we've got a circle and we can draw a line in it or outside it. So we've got three different situations if we draw a line on the equation, on the circle I mean. I can draw a line that goes through 2 points. Okay, I can draw a line that touches it once, so it intersects once. Or I can draw a line that doesn't touch it at all. So three situations, it can either touch it twice, once, or no times at all. So if 2 points of intersection, so if we touch it twice, we actually call this a secant. And a line segment joining these 2 points, so this point here and this point here, is going to be called what we call a chord. Now, 1 point is what we're actually interested in at the moment, and it's called a tangent. And they're exactly 1 point of intersection for a tangent. So here's one example that I've drawn. Another example could have been this one here, where it touches it once there. There's many different ways I can draw a tangent. Same with the secant, where it touches it twice. There's lots of different ways I can draw a straight line that touches the circle twice. But tangents are interesting, and we'll look at more on tangents in calculus, which is a later chapter. But at the moment, we'll just go through basics, and our fundamental starting point. So the tangent line is perpendicular to the radius. So looking at this one here, it's going to be perpendicular to the radius, meaning that it's at right angles. So the gradient of the tangent and the gradient of the radius drawn to the point of contact must satisfy the relationship, the gradient m of the tangent times the gradient m of the radius is equal to minus 1. Now this comes up every now and again. It's not common, but it is important, and we tend to forget about this. So gradient of the tangent times the gradient of the radius is equal to minus 1. I'm not going to go into why that is at this stage, so just remember gradient of one times the gradient of the other is minus 1. So example 6. Okay, we've got a circle with equation x take 1 squared plus y squared equals 5. We want to determine the equation of the tangent at the point 2, 2, and on the circumference of the circle. So if you notice, when I read out the question, every point, so I said the equation of the circle, so I wrote out my equation, okay, and we want to determine the equation of the tangent at the point 2, 2, okay, there's a good bit of information there. I might need to use it, so I write it down. I don't need to rewrite the whole question, just pick out the points that are relevant or important that I might be able to use. So that's what I do every time I read a question. Rewrite your equation and put any information that I might need. So what are we trying to find? So we want the equation of the tangent. Okay, that's what I want. So how do I do that? Well, starting point might be useful to draw a diagram. So we've got a center at, it doesn't move up or down, but it moves to the right once. Okay, and we've got a radius of square root of 5. So something that looks like that. So my center at 1, 0. Now, my point 2, 2 sits somewhere over here, roughly. So the tangent at that point would look something like that. And my radius from that point to the other point is going to be at right angles to it. So we say, let C be the center. And our center's at 1, 0. And we want the P, the point 2, 2. So the tangent is perpendicular to the radius CP. So my gradient of the radius CP is going to be equal to, now how do we find gradients? I'll just write it down this once. So it's either rise over run or y2 take y1 over x2 take x1. y2 is going to be 2, y1 is 0, x2 is 2, x1 is 1, so we get 2. So my gradient, CP, or the radius, is 2. Now I can say m of the tangent times m of the radius, CP, is equal to minus 1. My gradient of the radius is 2, so I can say m of the tangent times 2 is minus 1. So my gradient is going to be minus 1 over 2. So the equation of the tangent line is, that's my gradient. And I want the equation of the tangent. So if you also remember finding equations, we can say y equals mx plus c, or y take y1 equals m of x take x1 plus c y take y1, which was 2 for our tangent. M, we just worked that out as minus a half. X take x1, which was again 2. And just rearranging that, so we get y equals minus a half x. Minus a half times minus 2 is positive 1, plus 2 is plus 3. So there's my equation of the tangent. Okay, using the point 2, 2. Okay, so that's part A. Now, part B, the length of the tangent drawn from the point minus 4, minus 5 to its point of contact with the circle R. So again, I'll just redraw our circle. We moved across once and got a radius of square root of 5. So I want the point of contact between the center and the point of contact at -4, -5. Okay, so I've got a point -4, -5 is not on the circle. So -4 is down here somewhere, -5 is, we'll say roughly here. So here's my point, -4, -5. Now I want the point of contact between that point and a tangent to the equation. So I'm drawing from that point, that line there. And remember, that tangent is perpendicular to the radius. And so from here, I can actually make a nice little triangle. Okay, so looking at that, I'll redraw that as that. And we've got R, C, and T. This is -4, -5. C is 1, 0. So using the formula for distance between 2 points. So we want the distance T to C. So you can say T to C is equal to -4 -1 squared plus -5 -0 squared. And that's equal to the square root of 25 plus 25, which is square root of 50. And we know that our radius is square root of 5. So we can say C to R is square root of 5, which is our radius. So now we need to find T to R. So T to R, we're just going to call that little t. So using Pythagoras, now we know this length, we know this length. So this length here is going to be square root of 50 so square root of 50 equals this length here plus this length here, which is t, we don't know, and we want the square of them. So square root of 50 squared is 50, square root of 5 squared is 5, and we've got t squared. Now taking 5 over, we get 45 equals t squared. So t is going to be the square root of 45. Again, I can simplify it as 3 root 5, okay, because square root of 9 times square root of 5 is square root of 45. Square root of 9 is 3, and we get 5. So that's what my t is. So the length of the tangent from the external point to the point of contact, so this point to the point of contact, is going to be 3 root 5 units. So that's part B. And part C, the number of intersections of the line y equals y plus 3x plus 4 equals 0 makes with the circle. Well, I can say, let's call this equation 1. Equation 2 is x minus 1 squared plus y squared equals 5, and that's from our initial equation that they gave us from the start. Okay, that's equation 2. Simultaneous equations. Okay, I can rearrange this as taking 4 across, that should be, and then y equals minus 3x take 4. So I'm just rearranging equation 1. So now I've got y equals minus 3x take 4. I'm going to substitute that value in for equation 2. So instead of y, I'm going to put minus 3x take 4. So y squared, so minus 3x take 4 squared equals 5. From there, I expand. So x squared, take 2x plus 1, plus 9x squared, plus 24x, plus 16, equals 5. Simplify it. I get 10x squared, 22x, plus 12 equals 0. Divide by 2, I get 5x squared plus 11x plus 6 equals 0. Okay, so there's a bit of a quadratic. So with quadratics, we want to find the discriminant. B squared minus 4ac. B squared is 11 squared, which is going to be 121. 4 times a, which is 5. So 4 times 5 is 20. Times that by 6, we get 120. So we get 1. Okay, and because our discriminant is 1, if we remember, if it's greater than 0, we're going to have 2 points of intersection. If it's equal to 0, we would have had 1. If it's less than 0, we get no. So because it's greater than 0, we get 2 points of intersection. And that's all they ask. Okay, so using the discriminant because we had a quadratic in the end. So that's circles. Have a go at exercise 6.3. A few questions on that. And that's it. Thanks.